Welcome to Shanti-Peace for Mathematics. Recall for the function y is equal to f of x of one variable. The concept of differentiability at point x0 is allow us to approximate the function f by linear function in the neighborhood of x0. Analytically, we say that if f is differentiable at point x0, it is equivalent to saying that f of x0 plus h is equal to f of x0 plus h into f dash of x0 plus h into epsilon h, which epsilon h is a function of h, where epsilon 1 h will tends to 0 as h tends to 0, and the expression, that is L of x, will be f of x0 plus h into f dash of x0. It's called the linear approximation, and this epsilon 1h is the error in that approximation. So as per the standard definition that you know, that is f dash of x0 will write as limit of h tends to 0 f of x0 plus h minus f of x0 upon h. So when you are applying this limit h tends to 0, so actually you are approximating this quantity. So that error will come up. So that error is written in this form, h into epsilon 1h. So that can be written as in this here is h, if you multiply h, that is, and if I am not writing this limit here, that is h into f dash of x0 equal to f of x0 plus h minus f of x0 plus some error terms would be there because you are not writing limit right now. So that error term is this that we have written here. So, and this quantity which we have here, L of x, this quantity, it is nothing but the linear approximation of the function, and this epsilon of h is the error in that approximation. Now with this idea of a differentiability for one variable, we can define differentiability for functions of two variables, or in general that same idea you can generalize for functions of 3, 4 or more than that variable. Let us have a function which is f defined over D, which is a subset of r square to r. If you want to say this is differentiable at point x0, y0 in D, if the following holds. So the first one, I can say both fx at x0, y0 and fy at x0, y0 exists. It means both the partial derivatives are exist. Second one, x0, y0 is an interior of the domain D, that is, there exists some delta greater than 0 such that x0 plus h, y0 plus k is also belongs to D for all mod h less than delta and mod k less than delta. Third condition, that is C, there exists epsilon 1 hk and epsilon 2 hk. That means they are the functions of h and k in that neighborhood such that x0 plus h, y0 plus k minus x0, y0 equal to h fx x0, y0 plus k fy x0, y0 plus h into epsilon 1 hk and k into plus k into epsilon 2 hk. So is actually a same definition for one variable. We have copied that idea and generalized it to it. What we have there, we have this, it is only a one variable is there, so that's why it is x0 plus h, then a value at x0, then these are the derivatives which multiply to this h, and then there is a error term. So here there are two variables, so that's why it is a change in that function. Whatever the change in that function is there, that is x0 plus h to x0 and y0 plus h to y0 plus k to y0, and these are the derivative, that is h into, in the x direction it had h, and in the y direction we have k, and these are the error terms you will have. So this way one can define the f is differentiable for functions of one variable. In some of the book they have defined this differentiability in this manner. It says that if z is equal to f of xy is a functions of two variable which is defined over D, which is a subset of R square, and this x0 y0 is a point in the D, then there exists some function a and b such that x0 plus h y0 plus k minus f of x0 y0 equal to h into a plus k into b plus h into epsilon hk and k into epsilon 2 hk, where this epsilon 1 hk and epsilon 2 hk will tends to 0 as hk tends to 0. Here is also the same situation we have. That means epsilon 1 hk, epsilon 2 hk has to be tends to 0 as hk tends to, because they are the error terms. Here what is the difference between this definition and this definition is just a differences about this a and b value. Here the value of a is fixed with this fx at x0 y0, and here fy at x0 y0, that is the value of b you have. That is just that change is there, otherwise the definition will be the same. Either you can write this definition or this definition, both of them are valid. Here it just they says that there exists some function a and b. Here they are precisely saying that the function which are there, which are nothing but the partial derivative of f with respect to x and the partial derivative of y at that point. Now we'll talk about, this is the definition. Now we'll talk about necessary and sufficient condition for differentiability. That means if you want to check whether the given function is differentiable or not, this is the main tool to discuss that. So let us say f is differentiable, f be a differentiable at x0 y0. So as per the definition, what we can say, this is true. That means this quantity will be true. So we can say that it is f of x0 plus h y0 plus k equal to f of x0 y0 plus h into fx at x0 y0 plus k into fy at x0 y0 plus h into epsilon 1 hk plus k epsilon 2 hk, where this epsilon 1 and epsilon 2 tends to 0 as hk tends to 0. Now what I am doing, I am taking this quantity on the other side. So this will represent as in this manner, f of x0 plus h y0 plus k minus f of x0 y0 minus h into fx x0 y0 minus k into fy x0 y0. What is left on the other side is h into epsilon hk and k into epsilon 2 hk. Now I will divide both sides by square root of h square plus k square. So that will gives you x0 plus h y0 plus k minus f of x0 y0 minus h fx at x0 y0 minus k fy at x0 y0 upon square root of h square plus k square, which is same as h upon square root of h square plus k square into epsilon hk plus k upon square root of h square plus k square into epsilon 2 hk. Now if I take the mod both side, so we'll have modulus here, and this quantity I can say it is less than or equal to epsilon 1 hk plus epsilon 2 hk. Why we can say that? Because this quantity, which is always less than or equal to 1, because you can say that h square is always less than or equal to h square plus k square. So h is less than or equal to square root of h square plus k square. So therefore h upon square root of h square plus k square is less than or equal to 1. And in the similar manner, k upon under root of h square plus k square is less than or equal to 1. Now if I take the limit both sides, the limit of hk tends to 0, 0, if I consider, then this quantity will tends to 0, because as per the definition of differentiability, this epsilon 1 and epsilon 2, they are the error terms, and that error terms will tends to 0 as h and k tends to 0. So as per this, and conversely also we can say the same thing. So what is the idea we have? If you want to check that f is differentiable at x0 y0, we can say it is if and only if limit of hk tends to 0, 0, f of x0 plus h y0 plus k minus f of x0 y0 minus h into fx at x0 y0 minus k into fy at x0 y0 upon under root of h square plus k square has to be 0. So if you can want to check whether the given function is differentiable or not, either you can go by definition or you can do this. So let's solve some examples related to it. Prove that the function f of xy equal to x square plus xy plus y square for every xy belongs to R is differentiable. So here we need to prove that this function is differentiable for every R, xy. Proving this by definition, I am going with this definition to prove this, and we'll solve one more example. In that we'll use this idea. So here let us try to solve this. What will be the f of x plus h y plus k that you have, because that is the quantity we have here, x0 plus h, y0 plus k, where x0 and y0 is a point. Here I want to prove that function is differentiable at every point. So that's why I'm starting with x plus h, y plus k. Now as per the definition, that is x square plus xy plus y square, that is the given function. This is x plus h square plus x plus h y plus k plus y plus k. Now if you expand this, so this is x square plus 2xh plus h square plus xy plus xk plus hy plus hk plus y square plus 2yk plus k square. Now I am writing whatever the term without hk first, that is x square xy plus y square. So that is x square plus xy plus y square I am writing first. Secondly, with x I am writing, so there are two terms with the x and which involve also h and k, so that is 2xh plus xk. The third one I am writing the terms with y and with which involve hk, so there are two terms are there, so that is h y plus 2yk. The last one I am writing all the terms without x and y, so that is h square plus hk plus. Now you observe the first one, the first quantity we'll have, it is nothing but the f of xy, because our function is given in this form. H from this two quantity, then we'll have it is h 2x plus y. Third one, if I common out k from this two quantity, then we can write out xk into 2y plus x. Lastly, if I common out h from this two quantity, then it is h into h plus k, and this I will write down as k into k. So what will we have here? This is I can write as f of xy plus h into a plus k into b plus h into epsilon hk plus k into epsilon 2 hk. So where, what is f of xy? You know it is x square plus xy plus y square. What is a? That is 2x plus y. What is b? Which is 2y plus x. What is this epsilon? That is error term. It is nothing but the, here it is h plus k, which is tends to 0 as h and k tends to 0. Epsilon 2 hk will be k as per this, which is also tends to 0 as hk tends to 0. That means, and this side is nothing but the f of x plus h y plus k. That means for any xy point, it will satisfying the condition of the differentiability. So thus what we can say is f is differentiable at point xy, any point xy. Let's have the another example. Let's say f of xy will given as x square plus y square sine 1 upon x square plus y square if xy is non-zero, 0 if xy equal to 0, 0. Now we need to check whether this function is differentiable at point 0, 0 or not. Prove that f is differentiable at 0, 0. Now we'll use the another way to prove this, that is this way. For that you required what is fx at 0, 0 and fy at 0, 0. First let us calculate them. So what is fx at 0, 0? By definition, first thing you just notice that this function is having a value at 0 is 0, and for non-zero points it has this value. So we cannot do the differentiation as we are doing this, because this is, if we are differentiating only this, it is defined for non-zero value. Here we need to find out the partial differentiation of that with respect to x at point 0, 0. So we have to go by definition. What is the definition of partial derivative? Let us recall that it is 0 plus delta x comma 0 minus f of 0, 0 upon delta x as delta x tends to 0. Now as per the definition, this will be the limit of, this is f of delta x comma 0. Delta x comma 0 will give you delta x square plus 0 sine of 1 upon delta x square plus 0 minus f of 0 is already given as 0 upon delta x, and delta x tends to 0. So you just observe that what will be the limit of delta x tends to 0. This is delta x into sine 1 upon delta x square, because one delta x is cancelled with this. So we'll have this one. This quantity sine is a bounded. So I can say that mod of delta x sine 1 upon delta x square will be less than or mod of delta x will be tends to 0 as delta x tends to 0. So that means this limit is 0. So that means fx at 0, 0 will have it is 0. Similar manner, what is fy at 0, 0, that also we need to limit f of 0 comma 0 plus delta y minus f of 0 0 by definition upon delta y as delta y tends to 0. Now you can just see that limit of delta y tends to 0, this is nothing but the 0 plus delta y as per the definition square sine 1 upon 0 plus delta y square minus f of 0 is 0 upon delta y. As you know that the function f of xy is nothing but the x square plus y square into sine 1 upon x square plus y square we have. So due to that we can have this, and this will gives you limit of delta y tends to 0. This is 0 plus delta y square, so it is delta y square actually. So 1 delta y is cancelled with this, so we will have delta y into sine 1 upon delta y square. But as I given you above, the same argument gives you this is 0, because mode of sine x is always less than or equal to 1 for any x. So that's why this will be bounded function, so that limit will be 0. So that means what we can say is f y at 0 0 is also 0. Now ultimately what we need to prove, that the function is differentiable. So for that I need to prove that limit of hk tends to 0 0 f of 0 plus h 0 plus k minus f of 0 0 minus h into fx at 0 0 minus k into fy at 0 0 upon under root of h square plus k square. Learning via video mode, you have to sit with the pen and paper. Otherwise, the above steps which I have written, you cannot understand. This is the definition, as we have discussed that the necessary and sufficient condition we have did, and in that we have put it the x0 is equal to 0 and y0 equal to 0. That will give. So every times it is better, what my suggestion is, that while you learning via video mode, you sit with the pen and paper and write down whatever I am doing. So this will gives you limit hk tends to 0 0. Now what is this quantity? The first quantity, that is 0 plus h 0 plus k, that is nothing but the f of hk, and we know that the f of xy function is x square plus y square into sine of 1 upon x square plus y square. This is the function. So according to this, this will be h square plus k square into sine of 1 upon h square plus k square minus f of 0 0 is there. F of 0 0 already given 0. Fx at 0 0 we have calculated, it is 0, and fy at 0 0 also 0, divided by square root of h square plus k square. Now what is, again you can see that limit of hk tends to 0 0. This is nothing but the square root of h square plus k square, because 1 h square k square is cancelled with this one. So here the just 1 by 2 left. So that is into sine 1 upon h square plus k square. Again by the same argument which I have did it above, that is this function, or I can say this will be the less than or equal to limit hk tends to 0 0 square root of h square plus k square. If I take the modulus here, and this will be the mode of that, and this is already 0, so that's why our objective is completed. So that means we can say that f is differentiable at point 0 0. I have solved two examples here, one of the by definition, another by the necessary and sufficient condition. It is up to you which method you like to apply in given example. Now I will do couple of theorem here. The first theorem, it says that about the existence of the partial derivative. So in the previous video we have seen that if f is continuous, it does not guarantee the partial derivative are exist or not, and if the partial derivative exists, it does not guarantee that the function is continuous or not. So that was my previous video. That problem we are solving here. That means the existence of partial derivatives, it depends on the differentiability. So with regard to that, let's have this theorem. Let D is a subset of R square and f be a function from D to R, and given that f is differentiable at x0, y0, which is also in D, then prove that fx and fy exists at x0, y0. That means if f is differentiable, then it's guarantee that fx and fy are exist. Proof. Let us have the proof of this. The converse of this result is not true again. So if the partial derivatives are exist, we cannot say the function is differentiable. So for that, let us have given that here f is differentiable at x0, y0. So as per the definition, what we can say, x0 plus h, y0 plus k equal to f of x0, y0 plus h into a plus k into b plus h into epsilon 1 hk plus k into epsilon 2 hk, where a and b are independent of hk and epsilon 1 and epsilon 2 tends to 0 as hk tends to 0, 0. So let us have this as an equation 1. Putting k equal to 0 in 1, what will we get is f of x0 plus h, y0 is equal to f of x0, y0 plus h into a plus h into epsilon hk. Because k is 0, so this term is 0, this term will be 0. Now this you can rewrite as f of x0 plus h comma y0 minus f of x0 y0 upon h equal to a plus epsilon 1 hk. Now if I take the limit both sides, so the limit of h tends to 0, so we'll have a limit here, limit of h tends to 0 will, you know that is h tends to 0 and k is already 0 we have, so this is already 0 here, so that leads to this will be a, because you know that epsilon 1 is always tends to 0 as h and k tends to 0. So this is a, and what is that? A is a some function, and what is it this side? It is nothing but the fx at x0, y0. So what we can say is the fx is exist. In the similar manner, putting h is equal to 0 in 1, we get, so if you substitute here h is equal to 0, this term will get cancelled and this term will get cancelled. So we'll have x0 y0 plus k equal to f of x0 y0 plus b into k plus k into epsilon 2 hk. Again, we'll simplify this quantity in this manner. We'll have b plus epsilon hk, and if I take limit both sides as k tends to 0, this quantity will be the limit of k tends to 0, and here is already 0 we have, so that's why this epsilon 2 will tends to 0 as hk tends to 0. So this will have the b answer, and on this side it is fy at x0 y0, because this is the definition of partial derivative of f with respect to x0 y0. So that means we can say that fx and fy are exist if f is differentiable. That completes the proof of this result. As I told you, the converse of this result is not true. What is the converse? Converse says that if fx and fy are exist, it does not implies f is differentiable. So that we can see by an example. So let's consider the example. fxy and consider as xy upon square root of x square plus y square if xy is non-zero, and f of 0 0 is defined at 0. So what we need to prove is, we need to prove that fx and fy are exist, but f is not differentiable. So to do that, let us calculate what is fx at 0 0. So as per the definition, this is f of 0 plus delta x comma 0 minus f of 0 0 upon delta x as delta x tends to 0. So this will be the limit of delta x tends to 0. This will gives you 0 into, so delta is, so this function is nothing but the f of delta x comma 0. So it is delta x into 0 upon square root of delta x square plus 0 minus f of 0 is already given 0 upon delta x. So this will be limit delta x tends to 0, 0 upon delta x will gives you 0. In similar manner, you may prove that fy at 0 0 is also 0. That I am giving you as an exercise to do. The next thing I want to prove that we shall show that f is not differentiable. That means I need to prove that limit of hk tends to 0 0, f of 0 plus h 0 plus k minus f of 0 0 minus h into fx at 0 0 minus k into fy at 0 0 upon h square plus k square will not equal to 0. This if I prove, then we are through. Then we can say that it is true. So for that, let us try to do that. Limit of hk tends to 0 0. What is f of hk? The f of xy given function is xy upon x square y square. So that is hk upon under root of h square plus k square minus f of 0 0 is there. So f of 0 0 is given 0 minus h into fx at 0 0 that we have calculated as 0 minus k into fy at 0 0 which we also have calculated 0 upon square root of h square plus k square. Now this is equal to limit hk tends to 0 0 0. This is hk upon square plus k square. This is the quantity. I just compare the power in the numerator. The power has the 2, so the numerator has the 2 power and the denominator also have the 2 power. So that means you choose your path h is equal to mk. If you choose this path h is equal to mk, this limit does not exist. So if it does not exist, that means it is not 0. So let this limit mk comma k tends to 0 0. What I'm taking the path along this. So this will gives you mk into k upon m square k square plus k square. So this is limit k tends to 0, m upon m square plus k 1, because k square will get cancelled. So the finally you will have m upon m square plus 1, which is depend on m. So that's why this limit does not exist. Okay. If the limit does not exist, we can say that f is not differentiable. So that completes the proof of that remark that the converse of the result is not true. That means if fx and fy are exist, it does not guarantee that f is differentiable. But yes, if f is differentiable, then definitely its partial derivatives are exist at that point. Now the next result is, in one variable case you have that every differentiable function is continuous. Here is also there is the same analogous of that result we have. It says that let f, which is a function defined over D, which is a subset of R square to R, be such that f is differentiable at x0, y0 in the domain D, then prove that f is continuous at x0, y0. So it says that if f is differentiable, then the function is continuous. Here given that the function is differentiable, so by definition we can say that there exists a and b such that f of x0 plus h y0 plus k equal to f of x0 y0 plus h into a plus k into b plus h into epsilon hk plus k into epsilon 2 hk, where this a and b are independent of h and k, and epsilon 1 and epsilon 2 will tends to 0 as hk tends to 0. Now what we need to prove? We need to prove that the limit function is continuous. We need to prove that this limit f of xy as xy tends to x0 y0 is exist and it is equal to f of x0 y0. So let us start with that quantity. Now in this limit I am just replacing x equal to x0 plus h and y equal to y0 plus k. So whenever x is there I am just replacing x0 plus h. So what is, so this is, I can say this is nothing but the x minus x0, y minus y0 will tends to 0 0. Can I write in this manner? This quantity I can write in this way because it's nothing but the same thing. Now due to this it will have h is equal to x minus x0 and y equal to, sorry, k equal to y minus y0. So that's why we'll have this limit will be limit hk tends to 0 0 due to this x0, x minus x0 and y minus y0 is hk. F of xy is there, xy, instead of xy I am just replacing x0 plus h and y0 plus k. That is x0 plus h, y0 plus k. Now as f is differentiable, this quantity I can rewrite as limit of hk tends to 0 0. That is, by definition of differentiability we can write f of x0 y0 minus h a, sorry, plus h a plus k b plus h epsilon 1 h k plus h epsilon 2 h k. Now as hk tends to 0 0, this quantity will tends to 0 because it is 0 into a, this will be 0 into b because both this quantity are independent of hk. And as hk tends to 0, the epsilon 1 will tends to 0, epsilon 2 is also tends to 0. Here we have k. So that's why this quantities also are tends to 0. So that's why what is you will have is nothing but the f of x0 y0 because this is already independent from hk. So only the answer is left is x0 y0, and that proves the our quantity, that is limit of f of xy is f of x0 y0 as xy tends to x0 y0. It also proves that f is continuous. So that means this is the proof of the statement that every differentiable function is continuous. The obvious question one should ask is whether the converse of this statement is true. The answer is no. The converse of the statement is not true. We'll see by example. So define a function r square to r as f of xy equal to xy upon square root of x square plus y square, as xy is not equal to 0, 0, and f of 0, 0 is already given as 0. See, this same example we have worked with the above example. That means for this also we use the same example, xy upon square root of x square plus y square. In this we already calculated what is fx at 0, 0 and fy at 0, 0, and we already proved that this f is not differentiable. So with that note, I need to just prove that f is continuous. We already proved that f is not differentiable. So that means there is a function which is continuous, which is not differentiable. So if I prove that it is continuous, this is the counter example of the converse of the statement. So you know that something you want to prove continuity, then you have to go by definition. For every epsilon greater than 0, there exists a delta greater than 0 such that mod of x minus 0 less than delta mod of y minus 0 less than delta implies f of xy minus f of 0, 0 less than epsilon. So I am starting with this side, that is, consider mod of f of xy minus f of 0, 0. But what is mod of f of xy? It is xy upon square root of x square plus y square minus f of 0, 0, it is given as 0, so that is 0. And if you convert this quantity into the polar coordinates, so that will gives you r square cos theta into sin theta upon square root of r square. If I substitute x is equal to r cos theta and y equal to r sin theta into this, if I substitute here, we have this. So finally what we have is mod of r cos theta into sin theta, because one r is cancelled with this, which is less than or equal to mod r. And you know that mod x is less than delta, mod y is less than delta, so mod, this will imply x square is less than delta square, y square is less than delta square, this will imply x square plus y square is less than 2 delta square, which will imply square root of this one will less than square root of 2 delta. That will imply r is less than square root of 2 delta. If this is there, then r square is x square plus y square. So that's why this is nothing but the less than square root of 2 delta. If you want this is less than epsilon, then you have to choose your delta will be less than epsilon by 2. So what we can say now, we say that for every given epsilon greater than 0, there exists a delta which is less than epsilon by square root of 2, such that x mod of x less than delta mod of y less than delta implies f of xy minus f of 0, 0 is less than epsilon. So therefore f is continuous at 0, 0, and that completes the proof of the converse of that statement is not true. Differentiability we already proved above. Now I am giving you some exercise here that you can try for yourself. Prove that this function x square y square upon x square plus y square whole square if xy is non-zero, 0 if xy equal to 0, 0. Prove that f is not differentiable at 0, 0. This is the first example. Discuss the differentiability of the following function. That is f of xy is xy raised to 4 upon x square plus y square whole square if xy is non-zero, and if f of 0, 0 is there, it is gives 0, 0. So with this two example, let us recall what we did in this video. We have discussed the differentiability of the functions of two variables. We define it by two ways. One of the sufficient and necessary condition with the help of the limit we have calculated. We have seen two theorems, very important theorem here. The first theorem says that if f is differentiable, then its partial derivatives are exist. The converse of this result is not true. That we have solved by example. We have seen the another theorem which says that if f is differentiable, then f has to be a continuous. Again, the converse of the statement is not true. That also we have seen by example. That's it for this video. If you like this video, please press the like button. If you have any comments, suggestions or a question, please drop down in a comment box below. See you in next video. Bye bye. Sayonara.